So as I said in the plenary already, the aim of this tutorial is mainly to give you a basic understanding of the main steps needed to conduct deep learning in R. And we'll try to go through the basic workflow, which is build a model, prepare data to get it into the model, then train the model, and finally predict with the model. And in addition to that, I have quite a few larger.
From just Control Plus.
Like this?
Yes.
And in addition to that, I have a few extensions that are considering the interesting stuff for remote sensing, like pixel-wise classification and getting a remote sensing image into a convolutional neural net and the results back out into a map of predictions. But as you see here, this is quite a lot, so don't get scared by that. The idea is really to go through this part 1 here and to give you a basic understanding on how to do these things in R, but also what the arguments and the commands that we're using actually mean, so that you don't just put in some activation whatever and you don't know what it means. So we'll also try to give at least a basic understanding what's behind these code lines. And the idea is then to kind of hopefully raise your interest in the topic so that you can, if you want, continue with this document even after the session. That's also why it's so long, because I wanted it to be as useful as possible also on its own, so without me standing here saying things. So I have quite a lot of descriptions put in there. And one other thing I have is that there are quite a few side notes, as I call them, and these side notes are for some background information that I kind of cannot really go into through this or during this tutorial, but I also just didn't want to leave you with some words, so I put some description of these terms then in side notes, and if you are interested in it, you can click on those side notes to get some more information. So for example, when I'll be talking during the training about loss functions, and that we'll be using the binary cross entropy loss function to calculate our error, I'll leave you with that for the tutorial, but you're interested in that, you can click on the side note here and get a bit more information how the binary cross entropy is computed and what it actually is. So this is about for things that I cannot go into right now, but that you might be interested in looking into later. So that's what's the plan for this tutorial. So as I said, the basic steps that we want to go through are building your model, preparing your data, training your model, and predicting with your model. And the scenario is the following. So our task will be to develop a convolutional neural network for mapping while-dryer extent, the extent of while-dry, which is a certain form of grass. Let me put it this unscientific way. I'm not a landscape ecologist, but we want to map this while-dry here that you can see growing in these patches here. And the reason is that this species is a species that can, if it becomes dominant in an ecosystem, it can be kind of have negative impacts on the biodiversity in these ecosystems. This is so it's a plant or a species that needs management and therefore needs monitoring. And this is a classical ecological monitoring task. One of the tasks that are the reason why these tools have gained so much interest, these tools like UAVs have gained so much interest in the field of landscape ecology. So this is the test area, and the training areas are a bit further to the north. These two images here. So you see all the data is very, very small. We have a very small toy example because we hope that this is kind of something that can be reproduced also on a laptop without GPU and so on. We won't even use all these, the whole areas here, but only a few subset out of these areas. So you will see later how many samples we have. So this is the scenario. And the first thing we have to do is to build the model. So coming back to this overview that I've already shown during the plenary, the first thing we need to kind of wrap our heads around is what is actually happening in such a convolutional neural network as we are going to build it. And as I said before, the idea behind these networks is that there are a stack of successive layers, and these layers transform the input data, so in this case a small subset of an image, into different representations. And these representations are hopefully useful in the sense that at the end we get a representation, for example in this case an output of one number that is kind of close to what it should be. And what it should be, that is determined during the training. So we hand over the network an input image and a corresponding label. So in this case we have a binary classification problem. We want to detect, is there a target object, is there wild dry in this image present or not? And we hand over, for the training, we will hand over these images and a corresponding label, 1 or 0 for target or non-target. And the model will then learn to transform or to conduct all these transformations such that as a result we get a number that is as close as possible to what it should be, 0 or 1. And the first thing we have to do is to assemble the model out of these layers. And we will go through these layers later on. First we will just add a few layers to build our model, which is kind of the first step. And in the Keras package, which is the package that we use, there are 2 ways to build models. One is the Keras model sequential function, and the other one is the Keras model function. Let me just check something. There's one thing I wanted to show you before that, before we start. Because that might be a bit helpful to understand what we're actually doing. So we are now using the Keras R package, which is our interface to the Keras API written in Python, which in turn is the API for conducting TensorFlow operations. So the actual low-level tensor operations are being done by TensorFlow, that's the backend. Then there's Keras, which is the API, the high-level API for TensorFlow. And then there's the Keras R package, which is what we use to get access to Keras. At some point, we will also use the TensorFlow package, which allows us to get access to directly the TensorFlow API. We will use that at 2 points in the tutorial. And we will also use another package called TF datasets that we will later use for preparing our data, for conducting the pipeline to prepare our data. So just that you know what I'm talking about when we'll later be touching at some points some Python stuff. So mainly we will be using Keras, as I said, or Keras.
TensorFlow, can you run it locally, or it's always API when you have it locally?
They have certain APIs, so you can also run it from several other APIs. Also, you don't need necessarily Keras, but Keras is very kind of popular for using TensorFlow. So as I said, there in Keras, which we are using, or Keras, I don't know how to spell it, pronounce it correctly. There are 2 ways to build models, and the one that we will mainly need is the Keras model sequential. So this is a model that, as the name says, is sequential in the sense that it has 1 input, 1 output, and a directed linear stack of layers. Something like in this image here. So 1 input, 1 output, and there's a directed stack of layers, so there are no connections between layer 1 and 10 or layer 4 and 2, but it's only layer 1 to 2, 2 to 3, and so on and so forth. This type of architecture is fine for the most part of this tutorial only when we want to build more complex model architectures. For example, having more inputs, more than one or more than one output, or we want to have specific connections between non-following layers within this model. Then we need the so-called Keras functional API or API, which allows us to build quite flexible different sorts of models. But for now, we'll stick to the Keras model sequential. Building a model with Keras model sequential is pretty easy actually. So you start with just initiating an empty model by just calling this function here, Keras model sequential. Let me see if I can do that here. So we start with building a model, and then we use certain functions for adding layers to this model. So here in this chunk, we've added the first layer, layer conv2d. That's a convolutional layer. And we'll talk about these arguments later. If you now get the summary of this model, we'll see that up to now, this model only has one layer because we have only added one layer yet. And this is going to get bigger and bigger as we add more layers. By the way, if you first...
font bigger.
Bigger? Mm-hmm. Oh, wait. Like this? Let me see if I can still see something. By the way, when you're first executing a code that has to do with TensorFlow or Keras, you might get something like this mean-looking code here. But that's not a problem. That is mainly TensorFlow complaining that it's not running as fast as it could, because we're not using. So I'm running here this in the Docker container that I provided for you, and we are using the installation that is as compatible to as many systems as possible. So we don't have GPU support enabled here, and also we don't have a specific version of TensorFlow that would be kind of optimized for a certain CPU, which is also possible, and that's mainly what these warning messages here are about. So as I said, we now have added one layer so far, and we've done that with the function layer conv2d, and just the same way we can also add other functions. So the functions that we're going to use is layer dense, layer max pooling 2D, and layer flatten, because these are the layers that we are going to need. We need convolutional layers, dense layers, max pooling layers, and flattening layers. And before we talk about what these layers are, let's just continue with building the model by just adding all the remaining layers that we will need. So I'll do that here. So it's all just, each line represents the adding of one of these layers. One thing that you might have noticed is that we are not reassigning the result of these functions back to the variable first model, which is probably a bit surprising for you. So we're just conducting each function here once, and that's because in Keras models are modified in place. So if you call this function here with this model, then this model is directly modified by this function. You don't have to reassign the result of this function here back to first model. It's just enough to call this function on this model. So if we now look at the result by getting the summary, I think I'll go back to the HTML for that here. Let me make it a bit smaller for now. You can see this is how our model looks like. So it's a bunch of layers. Each layer has certain parameters and a certain output shape. And what these output shapes mean is hopefully going to get clearer as we proceed with this tutorial. So you can see we have convolutional layers, max pooling layers, flattened layers, or one flattened layer and two dense layers. And let's check what these layers actually do. First, a dense layer. So what dense layers do is pretty simple. They consist of a certain number of units, and each unit calculates a weighted sum of all the input values it gets, adds a value, and then returns the output. So coming back to the figure here, this would, for example, be a dense layer with one unit, because it takes all these input values here and returns one output value. And it does that by building a weighted sum and adding a number and then giving back the result. This weighted sum and the so-called bias that is added, these are the parameters which the model, or this layer in this case, learns. So all these layers, as I said, learn certain weights in order to transform the imagery in a way that it's as close as possible to the result.
So if you look at the last dense layer model, which you see here, this is the layer that we have added last, this one here. And as you can see, it has units equals 1, so this one has 1 unit, which means it will return 1 weighted sum. The dense layer before that has 256 units, so it will return 256 weighted sums. In other words, this layer takes the input values and transforms them in 256 different representations of those values. It's kind of extending the feature space to look at. And again, all these weights for all these weighted sums that are being calculated there, that's what the network actually learns. And in principle, we could just build a model only of dense layers and train together a lot of dense layers, which would then produce all kinds of representations of the input data, and then at the end give us an output. And we could also process images with such a network. The problem is that dense layers, as we build them here, would in this case only look for patterns in the whole image. So if you put an image into a dense layer, that means that each pixel value is one value that is kind of put into the layer to compute the weighted sum. So that means if you train a model like this with images, that can only detect patterns that are within the whole image. So they cannot detect local patterns, and these patterns also have to be in the same spot on the image. So they cannot detect local patterns either on their location in the image. And that's what convolutional layers are for. Convolutional layers are the second layers that we're going to talk about, and convolutional layers you've probably already heard about because they're not that much different from what you do when you do feature extraction manually. For example, if you're running an edge detection with a solve filter or something like that, that's a convolution. And convolution means that you have a certain filter kernel, like this one.
Okay. So all the pixels where you can center your image, where you can center this kernel around, are within this yellow box. And what's happening then is that each the weighted sum is built of each of these pixels within the moving window, and the weights for this weighted sum come from the kernel. So the first output here would mean input 1 times weight 1 plus input 2 times weight 2, and so on and so forth. So it's a weighted sum of all the input pixels within this filter with the weights coming from the kernel. So the next position here would be with a window from here to here. and then this is where the weighted sum is being built. So I guess you get the meaning. What this does is, depending on how these weights are configured, it extracts certain features from the input image. For example, edges. So this is an example of the first two convolutional, or the first two channels of the first convolutional layer, and what they do to this input image, for example. You can see that they are extracting different types of features. Channel is, I forgot about that. So each layer is not only running one filter, but multiple filters on the image. So that is kind of equivalent to the units of a dense layer. So for example, the first convolutional layer here, we said it should have 32 filters. This is what we specified here, filters 32. That means that it's not only running one kernel, but 32 kernels, 32 different feature extractors over the same image. And then the output is a so-called feature map with 32 bands, each band representing the response of one of the 32 filters to the input image. And that's why we have an output of 32 in this case. And here I have only plotted the first two of these 32. So we now have looked at two filters, the dense, two layers, the dense layers and the convolutional layers. Both of them extract information from images by transforming those images. And how this transformation happens depends on the weights of these layers. And that is what the network learns. And it learns this by being exposed to actual data and the corresponding labels, as I showed here. These layers that have weights that need to be learned are also called, or we just say that those layers have certain states, while the rest of the layers that we're going to use don't have a state. They're called stateless because they don't have any weights to learn. You will see that later. So one of these is the max pooling layer. What a max pooling layer does is basically sampling down the resolution of the input image. So as you see here, for example, this is a max pooling with a 2x2 filter. It slides again a moving window over the input image, but it doesn't compute any weighted sums or anything. It just takes the maximum of the 4 pixels within this window and outputs that as the output of the new tensor. So this value here will be the maximum of those 4. So it's a simple downsampling. And the reason this is done, or there are mainly two reasons for using max pooling layers. One is to reduce the size of the feature maps so that you don't blow up your network, because as you've seen with all these filters that are kind of added by the convolutional layers, your feature maps are getting bigger and bigger. And one reason to do this max pooling filter is to reduce the size a little bit. And the second reason is that the following convolutional layers that come after this max pooling layer will look at a larger spatial area, because remember that the input of such a max pooling layer could be the output of a previous convolutional filter or convolutional layer. So we have here the response map of this convolutional layer, which is then aggregated, and then the next convolutional layer looks at this aggregated feature map, so to say. And thereby, each convolutional layer later in the network looks at a larger, more complex pattern indirectly. And that's the second reason for doing these max pooling in between. So it's a pretty common thing to have in your network combinations of 1 or 2 convolutional layers and then one max pooling layer doing the downsampling, and then again a few convolutional layers, and then again a max pooling layer, just as we have done here in this sense, in this example. We have one convolutional, max pooling, convolutional, max pooling, convolutional, and so on and so forth. What all these combinations of max pooling and convolutional layers do is they extract increasingly complex but also increasingly abstract patterns from the image, increasingly abstract features. That means also if we look at the intermediate results, they become more and more difficult to interpret what is actually extracted there because they are more and more abstract. And these more and more complex features are then fed usually into a dense layer, which is then doing the actual classification, classifying the input based on all these features that are fed into the dense layer. And the last layer that we need to talk about is the flattened layer. This is more a technical thing. As I said before, a dense layer is doing a weighted sum of certain input values. And technically, these values need to be one vector of data, just one row of numbers. And what we get out of a max pooling or a convolutional layer is a 3D tensor with pixel rows, pixel columns, and image depth, like how many bands do we have. And a flattened layer just puts all these values one after the other into one long vector, which is then processed by the dense layer. So that is more like a technical thing. So to sum up, we compute or we assemble our model using convolutional and max pooling layers in combination for extracting certain local features of growing complexity. And then we put this into, or then we add dense layers for using these features for classification. And one thing that you might have asked yourself is, what about this? What about these arguments here? So we've talked about these functions for adding layers. And the first argument is clear. That is the model to add, to which we want to add this filter or this layer. And then for the convolutional filters, we have another convolutional layers. We have another argument, filters. That is how many filters this layer has. This is meaning how many different features are being extracted. Then there's a argument called kernel size. This is simply the size of these sliding windows. And then the convolutional and also the dense layers both have an argument called activation. And we set it to ReLU all the time, except for the last one, which is Sigmoid. This activation stands for activation functions. And the reason we need these activation functions is that all the transformations that we have talked about up to now are all linear transformations. So building weighted sums and adding a value, just as building the weighted sums within this kernel, are all linear transformations. So if you stack all those transformations together, the result is still one linear transformation. So we don't gain anything if you stack multiple layers all together. If in the end we still have one linear transformation, our network would still not be able to learn more complex representations of the data and thereby not be able to kind of conduct more complex classifications. Pardon? How do I define the number of filters? That is a choice of how you, so there's a choice of the architect of the network, so to say. And there are several kind of best practices, but I wouldn't feel in the position to judge which is the best one. But what you have to keep in mind, of course, is that the more filters you have, the more parameters you get. So I would say as many as needed, but as few as possible. Because the more filters you have, the more parameters you have. And usually, I mean, if you look at this, where is it? At our first model, which is still a pretty simple one, we already have 1.4 million parameters, which is quite a lot. I mean, if you come from
statistics or spatial statistics, you find this a ridiculous amount of parameters. But it's, for deep learning, it's still a low number comparable. Where was I? Okay, so all the transformations that we've done so far are linear transformations. And in order to enable our model to also learn nonlinear representations, we need activation functions. And this is what we define by this activation argument. What activation functions do is they take the output of these operations that I've shown before, so the weighted sums plus adding a bias, or these weighted sums within the filter kernel. These are actually not the final output of a layer, but instead these outputs go into an activation function, which then transforms those values nonlinearly, and the output of these activation functions is the final output of a certain layer. And which activation functions to choose? It's not an easy choice. There's quite a bit of thinking behind that, and we cannot go into detail here. I have a side note with a bit more of explanations about this. As far as this tutorial is concerned, you can just remember that these two are the main activation functions that we are going to use. One is called ReLU, rectified linear unit, and the other one is called Sigmoid. So the Sigmoid activation function, what this does is pretty easy to see. It takes the input value and squeezes all the values between, or in the range between 0 and 1. So you can see for large negative values, it's almost 0, and for large positive values, almost 1, and then here's this transition between them. The other one, the rectified linear unit, simply outputs a 0 for all values below 0, for all input values below 0, and for all positive values, it just adds the linear transformation, like it adds the same value. And again, the reason for using these activation functions is to introduce nonlinearity into the model so that it's not just learning linear representations. Both these activation functions have advantages and disadvantages. You could, or you should look into the side note on the vanishing gradient problem, which I also don't want to talk about now, but that is kind of related to the type of, or it's amongst other things also related to the type of activation function you use. But for our model, or actually for all the models that we will use here, we will use the rectified linear unit for all the hidden layers. Hidden layers are layers that are not input or output, but the layers in between. So these layers here. And we'll use the sigmoid activation function for the final output layer. The reason why we use the sigmoid activation function here is because we have a binary classification problem. And for such problems, the sigmoid activation function is a good activation function for the output layer, because as you've seen, it outputs a value between 0 and 1, which can then be interpreted as the probability of the image containing the target or not. So in our case, the image containing a wild, dry patch or plant or not. So, for example, the output of the convolutional layer that I've shown in this figure here doesn't actually not look like this, but rather like this. So all the result of the sum is put into the ReLU function, activation function. So this is a summary of the model that we've built. I'm not sure if you can see the gray boxes on the screen. So actually they are meant to be gray boxes here. You can probably see them at least on your computers. And this summary or this overview is meant to kind of briefly summarize what the model is doing. So the green arrows here symbolize convolutional layers. The blue arrows symbolize max pooling layers. The purple one, the flattened layer, and the orange ones, the dense layers. So this is how our model looks like. The gray boxes are the intermediate results, and the numbers on the left or right of these boxes or images are the spatial extent, the pixels, and the numbers on top of them are the image depth, the number of
layers or the number of bands, not layers, the number of channels or bands of the feature map. So for example, here, this is the input image. It has 128 by 128 pixels and 3 channels. It goes into the first convolutional layer, which transforms it into 32 feature maps, each with 126 by 126 pixels. The reason why it's getting a bit smaller is because, as I said before, this convolutional kernel cannot be placed over all the input pixels, because on the edge of your image, you don't have any neighboring pixel anymore to calculate the weighted sum on. So as you see, we have a sequence of convolutional and max pooling layers. And then at some point, we end up with an intermediate result of only 6 by 6 pixels, but 128 feature maps of those with that amount of pixels. And then we have a flattened layer that transforms this into just one row of 4,608 values that are then fed into the dense layers. And the first dense layer does 256 representations, doing 256 weighted sums. And then the result of this goes into the last dense layer that only has one unit, which means it takes all these values and computes one weighted sum that then outputs a certain number between 0 and 1, representing the possibility or the probability of that image here containing the target or not. And again, I mean, this is all the weights that are involved here are just learned during training. So we expose this network to ideally a very large number of images and according labels, and then it learns all these weights that are involved here, such that the transformation of an image results in something that is pretty close to what it should be as with respect to the label. So if the label is 1, then it should predict something pretty close to 1, and so on and so on. And this training is what we'll look at later. So this is how we built the model, and I hope you also got at least some basic idea about why we choose different, or at least what we choose when we choose different parameters here. So filters are the amount of filters, how many different feature extractors are applied. The same is true for units for the dense layers. So each unit does one weighted sum. Activation defines which activation function to use, and these sizes determine the size of the kernel. So the filter kernels are 3 by 3 pixels, and the pool, so the size of these max pool windows is 2 by 2 pixels. So also, as I showed here in this figure.
I'm quite sure that your case 0.93 actually represents.
This 0.93 can be interpreted as the probability that this image, or how certain the model is that this image shows a target or not. So 0.93 means it's pretty sure, or you can be pretty sure that there is a target in this image. And the reason is that it is trained with images where, or with data where images that show the target get the label 1, and those that do not show the target get the label 2. And then the weights doing all these transformations are trained such that all images in the training data that show targets are, or result in as high as, or as close to 1 as possible number by these transformations, and all those that do not show image, the target, kind of are transformed into a number as close as possible to 0. But how this is done, we will see during the training also.
So in your language, target is just whether some species, for example, is or not of some.
Exactly. So this is a binary classification problem, so it's only yes or no for the certain of the. Yes, so you can also do multi-class classifications, something that we don't talk about here. The result is that you would then use another activation function, for example, for the output, not a sigmoid, but a softmax, which is kind of the multi-class version of the sigmoid. But that's also possible. But here in this tutorial, we are always only talking about binary classification, like detecting a certain object.
Sorry, my question. So the 0.93 means that probability is one big maximum.
Yeah.
That you have detected one species in your 128.
In this image, yeah, or a subset, yeah.
One is there, or
Yeah, it does. I think you could translate it like there is a pattern visible there that makes the model think, or that makes the model react to this quite highly or with a high number. Yeah, or some part of it. That's actually a problem later on, because we have, of course, not only images where there are only target, where the full image is full of this target, or where there's none, but also maybe where there's half target and half background. But that's something that we'll get to later.
Yeah, but can it differentiate between the 2, 3, 8, and the?
No, not at this stage.
It's just a binary stuff.
Yeah.
Is there, or is not?
We will later see when we do this pixel-wise classification, that it also looks at where in the image are. Yeah.
What criteria do you decide which type of values to put and how big these will be described?
No, it's not just trial and error. There are, I mean, I'm not a good model architect, so I don't have a lot of experience there, but there are certain rules what you choose. And some rule of thumb is that this mixture of max pooling and convolution layers to extract the features. And what I've so far mainly looked at is not to get too many parameters, not to blow up the model too much. But usually there's this workflow. You start with a certain architecture, you test it on your test and validation data, and then iteratively improve it.
The strategy, is better to go with a simple setting, so minimum parameters and then increase, or is it better to go other way around, lots of parameters and then decrease?
That's a good question. I don't know if there's a kind of best practice about that.
In theory, maybe you come to the same.
Yeah, it could be. Yeah.
But it could be that it's more computational to go from complex to more simple. Because
Probably.
It could be that actually simple.
I mean, yeah, and usually you have much larger data sets where it also takes a while to see how good a model is if you kind of run it. But to be honest, so I'm looking at it from the application side, and we will get to that, or at least I will give a outlook on that later in the extensions, which is kind of using models that are kind of established or that have proven to work well, and use those models, sometimes even pre-trained for the certain application use case. So I will, as I said, okay. I will at least give an outlook on this, because you can also use pre-trained networks that have been trained on completely different input data, and use at least a few layers of those models for your use case at hand. See that later. So far what we've done regarding our code is only we have built our model with these functions here. At this point, I can also show what would be the next step. I'll for now kind of not show the preparing your data part, but only what would be the next step with the model. So we have only used a few lines of code here to build the model. If we later train our model, there are only two functions that we need. One is compile, where we define certain models for the training, parameters for the training, and then the fit function. And then after that, we only need one more line to predict, and then we're done with the prediction. So the actually only slightly tedious part now is the data preparation. as usual when doing when working with data. So we've now built a first very simple model, and now we want to prepare our data in a way that it can be fed into this model to detect the target. And the first thing we got to do is we just organize our data into training and validation, and into target and non-target. But this is nothing special here. So all we do is, so at this point, we assume that the data is already prepared. It's sitting on our desk. We have one folder, as it is also in the tutorial training data folder. We have one folder with images showing a target, and one folder with images showing something else, not the target. So we'll first read in the images showing the target. We'll add a label of 1 to those, and we build a data frame. Let me just do that here. Let me just go to that. So first can you see that? Yeah. First we extract the file paths to the images showing the targets, and then we create a data frame that looks like this. So it's simply in the one column we have all the images, and in the other column we have the label. In this case, all ones, because we have up to now only loaded the data that shows targets. We do the same for the images not showing targets, and then we merge these both to one data frame. So you can have a look at how it looks now. So it's a large data frame with targets and non-targets. And at this point, it's only the file paths to those images and the corresponding labels, because the actual reading of the data will come later. What we now do is we use the function initial split. I don't know if you've heard of that from other occasions or other use cases of the reassemble package, which splits our data into training and validation per random. And the two arguments that we're setting here is the prop, which is the proportion of training data. So I set it to 0.75. So we will have roughly 75% of all our data assigned to the training data and 25% to the validation data. And we use the column label here, the right column, as a stratum for this split, to make sure that the zeros and ones are split in the same proportions, so that we have the same proportions of, or roughly the same proportions of 75 to 25% for the target and the non-target. Because if you do it completely random, you could end up having almost only targets in the training data, for example, and the rest is in the validation data or something like this. So to ensure that you have the same probabilities in the training and validation data. The result then looks like this. It's an rsplit object. Can you see that? I also have it here. You can see it has, in total, we have 287 samples. 216 of those are in the training data set and 71 in the validation data set. And you can also look at those if you want to access either the training or the validation data set. You can do this with the function training on data for the training data and the function testing on data for the validation data. And we could, for example, check if this equal split has worked out. If we just count how many or if you look at our training data and count how many samples with label 0 are there and how many labels with label 1, and we see that they are both 108. So we have an equal split within the training data. We have just as much zeros if we have one, as we have ones. So the same is also true for, or almost true for the validation data, which is what we want. So you don't have an over or under representation of one of the classes that we're looking at. So up to now, we've only organized the data. Now that the part that's now necessary is to actually read the data into something that can be processed by our convolutional network. And in Keras or TensorFlow, we are working with so-called tensors. And tensors are kind of a generalization of vectors and matrices and so on to an arbitrary number of dimensions. And for the type of data that we are concerned with, I've tried to translate it into something that we know from R. So there would be a 0D tensor. It's just one number, it's a scalar. A 1D tensor is a vector. A 2D tensor is a matrix, and a 3D tensor or any higher dimensional tensor would then be represented by multidimensional arrays. And one thing to keep in mind here, or to kind of notice, is that the data sets in convolutional neural networks are not processed all at once, but in batches. So that's something that we will later determine how large our batches will be. So they will never, or usually you don't feed the whole data into the network, but only a certain batch of data. For example, first 10 samples, or not the first 10, they're randomly distributed, but a batch of size 10. And this is usually the first dimension of the tensor. So when we're working with images, as a result, we are usually working with 4-dimensional tensors. The first one is the number of samples. The second one is the number of rows. The third one, the number of columns. And the fourth one, the number of channels or bands. So for example, a tensor of shape 2, 4, 4, 8, 4, 4, 8, 3 in this example here would mean that it holds 2 images, each having the size 448 by 448 pixels and 3 bands. So let me catch up with this here. So as I said, we need to get our data somehow into the form of these tensors as it's needed by the convolutional neural network. And for this, there are several ways to do that. So Keras has some pre-processing functions, but here we are using the TF datasets package, which is a package that kind of provides access to the kind of a pre-processing pipeline for data that as it is needed for convolutional neural networks. And the first function that we're going to use here is called tensor slices dataset. Let me just execute that. What this does is it creates a so-called TF dataset object from the input, in this case, our training data. So the data frame holding all the images and labels of the training data. And the TF dataset, again, consists of a number of elements, each element being a pair of training data. For example, one element is one image and the corresponding label, and in the form of tensors. So one thing, if you've worked with Python before, you may know the concept of Python iterators. That's something that's a bit daunting, so I will not go into detail here. I have another side note on this. But a TF dataset is under the hood a Python iterable. So you cannot easily just plot it as a list as you would think it should be possible. But you have to use the Python functions as iterator and iterate to get access to single elements of a TF dataset. So I can show you how that looks like. But this is just for us. So we don't need a list or something. We need a TF dataset for the further processing. But if we want to inspect the dataset, then we can use this just to check how it looks like. So what I've done now, I've used the functions as iterator and iterate to kind of create a list of this TF dataset. And this list shows then the single elements of the TF data set. And each element, as I said, is again a list of 2 tensors, one for the image, you see this here as image, and one for the label. So this is just for us to check. I've also only plotted the first, I don't know, 6 or so elements. However, as of now, this tensor, as you can see, for the image is still only a string, because up to now we still only have the file paths. We haven't read any data yet. So this is what we are going to do next. So let me go here. And yeah, as I said, the data preparation is the most tedious part usually. So I will try not to go too much into detail, but just show the kind of the minimum that we have to do. So we need to read the images. Then we need to convert them into a float and into numbers between 0 and 1. So we normalize or we rescale values. That's something that is necessary, or at least it's advised, in order to help the network to train properly. Again, I have a side note on value normalization here that you can read to get further information about that. And the third thing we do is we resize the images. That's something we don't need in this case, actually, because the data, as I've prepared, it already has the correct size of 128 by 128 pixels, as the network expects. But if that was not the case, then they would be resized here into this predefined size using interpolation, using different resampling techniques. So these are the 3 steps that we got to take. And we do that using the dataset map and list modify functions. Dataset map is a function that helps you to apply a certain function on each element of a TF dataset. So if you say, for example, read file and decode JPEG, and we put that as a function into the dataset map function, then this function is going to be applied on each dataset, each element of a dataset. So let me show this here. We call the function dataset map on our training dataset, which means that on this dataset, on each element of this dataset, the following function is being applied. And the function that we applied is list modify. Because again, as I said before, each element of the dataset is a list with 2 elements or 2 items, the image and the label. And the function list modify allows us to modify a certain item of the list. In this case, we want to modify the image item. And that's why we use list modify. And the item that we modify is image, and we modify it by these functions here. And this is another thing that might be a bit strange to you, using these dollar operators. This is what I said before, where we use the TensorFlow package to get access to the TensorFlow API and use functions of this API for reading the data. And the functions that we use are read file and decode JPEG. So we first read the file and then decode it. We use decode JPEG because the images are stored on the disk as JPEG. And we modify our image list item by the result of this, which means that after this function, let me do this, we read in the imagery. The second step is, as I said before, change or transform the data type into floating point values. And then the third is to resize them. So the idea is always the same, just the function that we apply using list modify on each element changes. First it's the decoding, then the data type transformation, and then it's the resizing. Then the last 3 steps that we got to do is we got to shuffle the training data set, because up to now it's ordered. We first read in only the images with label 1, like all the images containing targets, and then all the images containing no targets. And in order to have proper training and not kind of start running the model only on target images and then later only on no target images, we need to shuffle them. And this is what Dataset Shuffle does. Then we use the function Dataset Batch to create batches from our dataset. This is what I said before. Then the data set is not processed as a whole, but instead it's processed in batches. And here in this case, we define the batch size 10. So in each step, only 10 images are processed, and then the next 10 images, and so on and so forth. And then the last step is unname. We need to unname our data set, meaning these names, image and label, are being removed. This is simply, as far as I know, a technical thing, because if we don't do that, then we get an error message in the next steps. We can now have a look at the resulting data set, just to see how it looks like and how we have changed it. So I'll go back into the HTML for that. So I've now done this iterator trick again to make the list out of this data set and check the first element of the data set. And of this first element, I check the first item, meaning the image tensor. That's what I'm looking at now. And this function gives you a very long result because it shows some of the actual values within this tensor. So you don't need to kind of pay attention to the exact numbers here. It's just kind of a preview. And it also shows you the shape here of this tensor. Oops. And the data type. And the shape is 10, 128, 128, 3, which means we're looking at the tensor holding the first batch of data. Batch size was 10. That's why the size of the first dimension is 10. Then the next two dimensions are 128 and 128. That's the size of each image. And the fourth one is 3. That's because we have 3 bands. And we see the D type, the data type is float, because we have changed that during the pre-processing. We can also, if you want to only look at the shape, for example, you could also use this $shape operator here so that you get only the shape, for example. We could do the same with the second item of the first element to check the tensor holding the labels corresponding to these images. That's a much kind of less complex tensor. It only has these 10 values, which are the 10 labels of these 10 images correspondingly. And it's a data type integer. And with this, we've prepared our data, which, as I promised, is a quite tedious process. But when you've done that, it's pretty easy to kind of feed this data into the network. You will see later when we do the training, we just throw in this data set because all the preparation has been done already. So we've done that now with our training data. Now we do the same with our validation data set. These are all the same functions that we're using here. The difference is that we don't need the shuffling because it doesn't matter if they are ordered or not, because we're not using the validation data for training. So the validation data will only be used to give us an idea of how well a model is performing after a certain epoch. You will see that. So I'll catch up on this. So now we have 2 TF data sets, one for the training data and one for the validation data. And with this, we can finally start training our model. And the training of the model, again, in terms of our code, consists mainly of 2 functions. One is the compile function and one is the fit function. The compile function, as you see here, needs a few arguments. The model that we want to compile. Compile means kind of prepare for training. And then in this case, we set 3 other arguments: optimizer, loss, and metrics. And these 3 arguments are kind of the keywords associated with the general workflow that is kind of pursued for training. And I've sketched this workflow here, how actually this network is being trained. The first step is It runs on one of these batches that we've defined. So each batch has 10 images in our case. The model is being run on one of these batches, so meaning on 10 images. In the first place, it has randomly assigned weights. So it will probably not make, the output that we get will probably not make much sense. But the output is being computed in the first step. Then this output is compared to the corresponding label that is assigned to each of these input images. And the loss is being calculated. Loss is kind of the error. How far off is our prediction from the label? And how to calculate this loss is what we define with the loss function. So here, as you can see, we have determined binary cross entropy as the loss function. And as I said before, I will not go into detail here how binary cross entropy works, but you can look at the corresponding side note to get additional information on that. What we also have to assign is the optimizer, because that's what's interesting in the third step. So we have computed the loss on a certain batch, and then the next step is that the perimeters, meaning all these weights of our weighted sums in the dense layers and of the kernels in the convolutional layers, are adjusted just a little bit to reduce the loss on that current batch. And the way how this reduction or this adjusting of weights is being done, that's what the optimizer defines. And the learning rate again defines, you could say, in what or how large the steps are in which we adjust these perimeters. Here's an I shouldn't have chosen gray because you can again not see quite a lot, but here's a kind of figure showing how this works. So as I said before, run the model on a randomly drawn batch, compute the results of the prediction and compute the loss, kind of how far off is the prediction for this batch from the labels, and then slightly adapt the perimeters using the gradient descent approach to reduce the loss. And then run the model on the next batch and do the same. And then iteratively reduce the loss always by adjusting the weights or the perimeters a little bit. And this adaptation of perimeters uses the gradient descent approach. So again, I'll not go into detail, but you can imagine it like this. The loss function, as I said, is computed, and the derivative of this loss function is computed. So the gradient. So you kind of get a loss surface, and you just go a little bit down the slope of this loss surface. So you kind of change the perimeters in the way where the loss is going down. So gradient is kind of the multidimensional version of a derivative. And this you do kind of for all the batches in your data set. And when the whole data set is finished, one epoch is done. And we can determine how many epochs we want to run, how long we want to do the training in the next function, the fit function. So here I have another description of these different arguments. One argument that I haven't talked about is the metric. This is, in this case, accuracy. This metric is not used for the training itself. It's just what we get out during the training as an input or as an information for us how well the model performs at a certain iteration. So in this case, we use the accuracy, which means binary accuracy, which is simply the fraction of samples, meaning of images, that are correctly classified. And by correctly classified, in this case, by default, this means a threshold of 0.5 is chosen, and everything above this threshold, so any output of the model above 0.5 is considered 1, and everything below 0.5 is considered 0, and then it is compared to the label, which is 0 or 1, and the fraction of correctly assigned images or samples is then calculated as the metric in this case. So this is what is specified with the compile function. And then we use the fit function to actually do the training. And what you see here is what we need as inputs here is the model that we want to train, the training data set, and the validation data set, and the number of epochs. So as I said before, if it runs in batches, and if all the data has been processed batch by batch, then one epoch is finished, and then next epoch starts again with the same data. And this is continued for as many epochs as we determine in the this method here, or in this function. Let me again catch up with that. I hope I haven't forgotten any type of code. So again, as you can see, there's a lot of kind of background that I'm that I cannot talk about here, like what is the mini batch stochastic gradient descent, but it's all in the document for you to read later on, because I'm pretty sure I also forget some things. So again, this is the method that we use to fit the model. The reason why so actually we wouldn't have to assign this to a result again, because it's modified in place. But assigning this to a variable in Keras makes the metrics for each iteration being saved to this variable. So we can later have a look at the metrics at different epochs. So I'll try to run this now. I hope I haven't forgot anything. Not sure if you can see that. So this is the first epoch here. These are the steps. Each one being calculating the loss and so on one batch. And then when it's done, the next epoch starts on the fourth, and on the right you can see the loss after each step and the accuracy. And also, so loss and accuracy is referring to loss and accuracy on the training data, which is the data that is being used to change the
GPU, right?
Pardon?
On GPU.
No, this is on the computer.
On the computer.
Because it's a very small, as I said before, it's really a toy example. I know that usually you would do this on much larger data sets, but this is the reason why I can show it here.
And is it parallelized automatically?
Yes, I think so, but I'm not 100% sure. But it's much quicker on the GPU. I have the GPU at home, and I can try to get access to that.
It's okay, don't have to do it.
Here, this is. I think I had prepared this.
You feel how off my computer setting here?
Are you following it?
Terrible.
It's parallel, okay.
I'm not sure if I have finished. Let me just try. I'm not sure if I had. So this is now my computer at home. It is running a kind of normal user gamer grade graphic card, but that's already enough to do quite a lot of stuff. I'm not sure if I had prepared everything. Let me see. Yeah, so it's running now, and you see it is much faster, so it's almost done. It's the same number of epochs, so it's done. And I think the other one is still running, yeah. But still, I mean, this is a 2-core, I don't know how many years old computer. So
How much is the one in the office?
this is a GTX 1080 Ti. I don't know if that tells you something. The graphics card, it used to be a quite decent graphic card 2 years ago, I think.
Okay.
But now they have a new generation, which I've heard has specific tensor cores. So it's kind of, yeah, the hardware is also getting even more optimized for this kind of stuff. But that's not my field of expertise. I don't know. So what you get as a result during this training process, you can see here also a plot of the validation accuracy and the loss. And as I said before, as I assign this to the variable diagnostics, then I can later look at the diagnostics, for example, to plot them. This is the result here on this, on what I've done just now, and this is the one that I've done before in the Markdown. And what you can see here is that maybe after like maybe 10 epochs, we might have stopped already because the values are not are not getting better anymore, not a lot. By the way, one aspect which is very important, but it's not covered in this tutorial, is the aspect of overfitting, which can happen quickly if you have that many parameters, of course. And just one note here is what you should look at when you do the training is how the training curve and the validation curve behave. So for example, if your training curve keeps on increasing, or the accuracy keeps on increasing, or on the other hand, the loss keeps on decreasing for the training curve, but the validation curve has flattened out already and it's not kind of improving anymore, then you're starting to overfit because the data is getting, or the parameters are getting fitted more and more to the training data without any effect on the validation data. Because remember, the validation data is not used for the training. This is just for looking how this model performs on other data than the one that is used for training. And yeah, if the accuracy on this data is not improving anymore, but it is improving on the training data, then it's basically overfitting. Okay.
In this specific case, you look at the blue line, and when it reaches the peak accuracy, the couple.
Yeah. However, yes. However, but in this case, we have to be careful with interpreting the result because of this small toy example with very low data. So if you try this, the curve might look quite a lot different to this one. So there's quite a high vulnerability, so to say, to changes in certain parameters, and so because it's a very small data set. You also see this these are the curves which are smooth, but if you look at single values, they're fluctuating quite a lot, especially in the training data set because it has even lower. It has only 25% of the data.
If you have this data set, you have millions of points.
Pardon?
If you have millions of training points, millions, and then hundreds of images.
Yes, it's possible. I mean, this is, as I said, a minimum example on a laptop. The other extreme would be running it on a Amazon Web Services GPU, for example, and then you can kind of do pretty large trainings. But I haven't kind of dived in this field yet.
Okay.
If you realize that you're overfitting, you just run the fit function again.
For example, but actually there are smarter ways which we also cannot cover in this tutorial. For example, you can configure the training with early stopping mechanisms that kind of you give as an aim 15 epochs, but you set certain rules for early stopping, like when the accuracy is not improving or only improving slowly or something like that, then it stops early. So that's something you can do. So now that we have fitted the model, we can use it for prediction by simply using the predict function. And the predict function just needs two arguments, our model and validation data set, or not validation data set, whatever data set we want to predict on. In this case, we predict on the validation data set in the first step. And what you get out in this case is just a matrix with one column that holds the corresponding prediction value for each image in the validation data set. So here the rows are the samples and the values here are the predictions. Because in this case we only have as an output 0 or 1, just one number. And here I have plotted 3 examples of images of the validation data set, and I put in the caption the prediction result, what the model puts out, and the label, what kind of is the ground truth. And you see that in this case, in these 3 examples, the first 2, these are kind of images holding or showing the target, and the prediction is also pretty high, 0.95, 0.97, and the last one, where the label is 0, also has a very low prediction. So that looks pretty good. But even more kind of interesting than doing it with the validation data would be to do it on a completely different data, which in our case would be the test data set, which, if you remember, is in the west of the image of this island. Oh, did I break it? This one? Okay. So what we do now is, or we use the model to predict on the actual test data. And this is what you see here. We again have to pre-process all the images. And as of now, we still assume that all the images are already kind of subsets in the corresponding size, and they're sitting on our desk. So we still only have to load them into Tensors. And we do that the same way we have done before with the training and validation data, using, it looks a bit strange here, but using read file, decode JPEG, and then convert image type and so on. What we of course don't need is the shuffling again, because we don't train on this data. So we basically only transform the data into the format that we need. And then we do the same as before. We predict using first model as the data set, and first model as the model, and the data set, which is now our test, the data set from our test area, as the data set to predict on. And we would then get again a number of predictions here. And in this case, I've turned these predictions already into a map, which then looks like this. So I've for now not shown the code for this here. It's of course in the markdown, but what it basically does is it reassembles first it turns the result into an array of the size of the corresponding image, all with the same value, which is the prediction value. Makes polygons out of them, and then puts them into the map. And this is what the result now looks like. I don't know if you can see it very well on the screen. Sorry. So on first sight, it doesn't look too bad, given that this is really a toy example. It's a quite small model and also a small data set, but it doesn't look too bad for now. However, there are, of course, certain issues with it. The most prominent one probably is the fact that, I mean, that is also what your question was referring to before. We are predicting it on the size of these tiles. So there's always there are always kind of edge cases where there's target and non-target, and our result kind of has a low spatial resolution. What we could, for example, do is decrease the size of these tiles, but that only makes sense up to a certain point, because we want to include the spatial context, and the more we reduce the tile size, the less we can include spatial context. And also we create a huge overhead. So sometimes the kind of reassembling of all these tiles to one map here takes longer than the whole prediction with the model. So what would actually be cooler than running this on tiles would be doing a pixel-wise classification. And this is what UNets do, and this is what would be the first sort of extension of this basic workflow. So let me just show you how the result would look like. This is here under final, kind of spoiling a bit. Final prediction result would then look like this. So this is if you do the pixel-wise classification. So let's get back to the prediction here. Yeah, sure. but I'm jumping, so I've skipped all that leads to this. I will kind of, I was planning to give at least an outlook on how to do this, how to get here.
So you just put the threshold 50% and then.
Yeah, but that's the same thing I did for the, I forgot to tell, that's the same thing I did here as well. So I excluded all the tiles that had a value below 0.5. And the rest of them still get the kind of color corresponding to how much or how high the value is. You could also do them all in one color, actually. Yeah, so I mean, I think we have 30 minutes left, and we've quite a lot of markdown left. But as I said before, I'm not planning to kind of talk about all this, but I was planning to give at least an idea of how that works, because that is another form of model architecture, which is, I guess, pretty interesting for us when we are doing remote sensing. So that I was planning to focus on that for the remainder. Are there any questions as of now regarding this basic workflow?
Is somebody using the chaos package in TensorFlow in R? Before, I mean, before. You have experience, so it's all new. Okay. Nobody? Well, that's interesting. That's a really good match, so we are completely new things, yeah.
Would you recommend using it directly in Python, or is it all packaging concept?
I guess if you're familiar with Python, there's no reason to use another backdoor to that. But for me, that is kind of the reason I could start using it, is that it is in R, because I have a tiny little bit experience in Python, but not enough to do that, probably. But
because there's no like training and it's not done in R.
Under the hood, it's all done in Python.
Yeah, yeah.
So there is actually, if you can do Python, why wouldn't you do that? And maybe let me just briefly summarize that. I think as I said before, the boring part is the preparation, but other than that, it's pretty straightforward. So we have built our model with these lines here, more or less, and these two. Then we have prepared the data, which is a bit more complex. And as I said, there are other ways, probably smarter ways to do that. I chose this one because I think it's quite intuitive to do it with TF Datasets package. Then the training is just these two functions. And then the prediction is, yeah, basically only one function. So that is pretty straightforward. And I mean, there's a lot of background to these, especially to the training part. I could only kind of scratch the surface there, but I do have a few side notes, and in the side notes there are also some additional links where to go to get a bit more info about that. And again, just keep in mind we have a very small data set, so this is not what you would kind of normally do or publish in the paper. This is really just to show you something that works also on a small machine, and that still shows some results that kind of can be visualized well. So there are certain things that can be done as extensions to that. One is, again, the pixelwise classification. Then two things that I wanted to just at least mention that are kind of interesting if you're working with EIB data, because these methods are good for handling or for tackling small data problems, is data augmentation and using pre-trained networks. Data augmentation I can just pretty quickly tackle. This means that you take your training data set, your images, and manipulate them so you create synthetic new images. For example, you can flip them, rotate them, you can do some elastic transformations, and thereby kind of emulate new data. And you can also change per random certain illumination conditions, like or spectral conditions like hue, saturation, contrast, and so on. And I have an example here in the markdown. I will not show it now, but I just want to mention it. And I've done that here in this example, and by that increased my my training data size by the factor 4. So I added 3 times the data set size with some augmentations. And then another technique for that is useful when doing or when working with small data sets is using pre-trained networks. Again, I will not go into too much detail, but I would like to at least show the idea that I mean. So the Keras package comes with a number of kind of well-established model architectures that you can just load, and you can decide whether to load them with trained weights or not. And you can sometimes choose on what data set these weights should have been trained before. And that is a pretty interesting tool, I think. So the function to use for this is application underscore and then something, in this case VGG16, because here we read the VGG16 model. This is a classical model, so to say. It's not kind of state of the art anymore because it's already quite old, but it's a pretty good model. And here we read this convolutional model, and we define the argument weights equals ImageNet. So we load the model that has been trained on the ImageNet dataset. The ImageNet dataset is a huge dataset, but it has the images in this dataset are mainly animals like cats, dogs, and everyday objects. But we can still use some layers of a model that has been trained on this data in our use case if we only use the first few layers. Because these, as I said before, these first few layers extract certain features within images like edges and certain shapes, and not necessarily too complex features or features that are too close to what it has been trained on. And since in our case we have also kind of target objects that are not too complex, if you have seen the input images, is mainly this grass, it might be helpful to use a few layers on a pre-trained network and then just add our own dense layers and then continue the training with this hybrid model, so to say, and freeze the weights of the first layers so that only the layers that we have put on ourselves, the dense layers, are being trained. This is what I'm kind of trying to show here. So this is the model that we had before, and we kind of replace this whole feature extraction part by layers from a pre-trained model, in this case the pre-trained VGG16 model. This is what it symbolizes, and this is how to do this. Load the model using the application VGG16 function, then we freeze the weights, and then we extract the first 15 layers of this model. This is done here by $layers and then subset 1 to 15. We write that to the variable pre-trained model, and then we add just a flattened layer and the 2 dense layers as we had before to this pre-trained model. So we now get this. And if we continue to train this model, only training the last 2 dense layers here, I've done that as well. And here I've done that only for 6 epochs, and you can see that after 3 epochs already, okay, this is very high. It's already an accuracy in the training data of 100%, and between 92 and 98% on the validation data. So it converges pretty quickly. And this is how the result looks like. I mean, it's hard to compare that now to the result before, but again, I wouldn't overinterpret the results anyway because of this small data set. This is just meant to show how this could work, so you can kind of take more time to try that on your own. How it works when you kind of use pre-trained networks or parts of pre-trained networks to increase your accuracy. And the good thing is we don't have a lot of data, but all these feature extractors we don't need to train. We just use the pre-trained weights already, which makes the result, of course, a bit more generalizable because it has not been fitted at all to our specific data set, so it cannot be overfitted to that data set. Yeah, it looks cleaner. So, well, we could look at some details, and I think it would kind of be a higher accuracy in total. But you can also see that it's much more certain about its decisions here. That there are higher values there. But again, it's it would be careful in interpreting single weights and so on. Okay, so this was just a very quick kind of ride through data augmentation and using pre-trained networks. Again, I hope that you'll find the HTML useful in getting more information on that. Now, as promised, we would like to talk about this pixel-based classification. And for doing this pixel-based classification or segmentation, we use an architecture called UNet, which has been proposed by Ronneberger et al., which maybe I can show you the original paper on that, if I find it quickly. So this is how the original architecture looks like. Sorry. So the first part is actually pretty similar to what we've used before. It's a sequence of convolutional layers and max pooling layers that, as I said, kind of successively extract more and more complex features. And if we would, for example, here at this point, after all these feature extractors, add a flattened layer and a few dense layers, then we would have a kind of traditional image recognition network. So we could put a sigmoid activation function at the end of the last dense layer and then get, again, a number between 0 and 1 for a binary classification problem telling us whether or not the target is in the image. But the unit doesn't stop there. But instead, at this point is where the second part of the U starts. So they start upsampling the image back to the original resolution of the input image. So let me get back to the HTML. Here, this is a very simple depiction with only 3 of these convolutions, convolution blocks. So when you're here down at the unit, or down at the bottom of the U, so to say, you start upsampling the data again to the original resolution, and so that you get at the end a result that has the same resolution as the input. But the trick here is actually shown or hidden in these gray arrows here, because the data is not just upsampled, but at each step, after each upsampling, the corresponding layer of the contracting path. This is how this part of the U is called, which the corresponding layer of this contracting path is concatenated to the corresponding layer of the expanding path, so of the right side of the U. Concatenated means they're seriously just concatenated, and this means that the following convolutional layers here take into account kind of this condensed information that has been that it has got out of all the convolution and max pooling convolution and so on. So it takes all this context information that has been learned, but that has not that does not have a lot of location information, because this max pooling reduces the resolution at each step. So it uses this kind of context information, but at the same time, they also get access to the corresponding information from the high resolution, so to say, layer of the contracting path that at this certain steps has the location information of the features that were extracted at this point of the unit. And this way, the model can better assign back the kind of the information or the detected features to the location where they are or have been detected. It's a bit difficult to explain, and probably also to understand, I assume, or I admit, but the result is that we don't get just an upsampled image, but an upsampled image that takes into account the location information about the features that have been extracted on the contracting path, so on the left side of the U. And the final form that we get looks a little bit like this. That's how they depicted it, and that's also why it's called UNet. So we have the contracting path, which has a lot of kind of abstract information extracted, and then we have the expanding path where the images are resampled to original resolution, but these resampled outputs are combined with the kind of location information from the contracting path to get a kind of better localization of features within the resulting images. And as a result, you can then kind of produce segmentation or pixel-wise classification. And I have an example here in this HTML as well, how to build such a model. This is how it looks like. I will not go into every detail, but what you can see is we have convolutional blocks. They consist of convolutional layers, 2 in this case, followed by a max pooling layer. We have, in this case, 2 of these blocks, so this is only this small example here. Then this is kind of the bottom of the curve, as I call it. This is here, these 2 convolutional layers, and then is where the expanding path starts. This is done by transposed convolution for the upsampling. Then this is the concatenate. This is what is represented by these gray arrows. This is where we kind of glue together the upsampled output and the corresponding layer from the contracting path. This is also done in this example twice. So we have concatenation here and concatenation here. And this is then followed by each time by 2 convolutions that can then, as I said before, take into account not only the distilled information from the whole model, but also the location information from the corresponding layer of the contracting path. And we can also combine this idea with the idea of using pre-trained networks, as I've shown before. So what I've done here is I use the layers of the pre-trained VGG60 network for the contracting path, for this feature extraction path, and then I just manually add the second path of the U. So in a sketch, it would look like this. Again, not that well visible on the beamer, but I think you get the idea. So we use this part of the model as a pre-trained model. Again, the model that has been trained on pictures of cats, dogs, pots, whatever, balloons, and add only the upsampling part, the expanding part. And with this architecture, we have so far gotten quite nice results, because this is also the one that I used here for this final prediction result. So what we have here, by the way, if you're doing this as well, I hope you haven't already started training this UNet, because that is something that the only thing that I would not do on a laptop. It takes a bit longer then. So that's, maybe I should have said this a bit earlier. I'm sorry. Yeah, so this is actually, so it will work. I've tried it, but only for 2 epochs because I didn't want to wait anymore. But this is something that still works easily or kind of performs easily on a GPU as the one that I've shown before. It then takes a few minutes only. Maybe I can, let me see if I get this prediction. If I can at least start it. Notice. Pre-trained. I'm just looking for the code chunks. No, this is the. Let me see if it works. So I include all this augmentation that I've shown before. I'm really running through it now. There is how much of it. So even the GPU is now complaining that it could be faster if there were more GPU RAM available. Now it starts training. Let's see how long this takes. Okay, one last thing that is actually, I think, quite an important topic, but again, cannot talk about it in detail, is inspecting your network, like getting a bit or shedding a bit of light into this black box that it still, to a certain degree, is. Because at least for these feature extraction paths, all these convolutional layers and so on, they are quite amenable to kind of being visualized so that you get an understanding of what your model actually has learned. And what you can do is, for example, here I'm again only trying to show the result more or less. What you can do is you can build a model out of only parts of your trained model, so that the outputs of this model are the activations of those certain layers. So you can get intermediate results and see how your trained model responds to certain input images. This is what's done here. I'm not showing this right now, but this is how the input image, for example, looks like. And here I've visualized, so you can try this as well. The function is in the HTML as well. I have visualized the first 4 channels of all the convolutional layers in this net. So you can see all the different forms of patches or patterns these layers react to. So this is how to use this function. Again, it's defined also in the code. You basically choose the image that you want to kind of see how, or the image of which you want to see how the model layers react to it. You put in the model, and you put in a vector containing all the channels or all the layers of which you want to see the results and the channels of all those layers. So here I've chosen layers 2, 3, 5, 6, and so on. And of each layer, channels 1 to 4. And so I get of all, in this case, these are all the convolutional layers. I get the results of all those. But each, only the first 4 channels of each of those. It's done. So this is, I should have taken the time, but as you see, that was how the GPU is now ready with this training already, so that didn't take too long. Again, this is, as I said, a quite small data set. For this example that I've shown here, we also did like more training on larger areas, and then the training takes about half an hour on this machine that I've shown. So it's still something that, at least at this scale, can be done on a kind of home computer. And then this is again what the results look like.